Hi, my name is Eckhard Ohlmer. I am one of the product architects for an ICE software-defined radio product line. Can't I just draw what I want to have in an RFNoC FPGA design, similar to drawing a signal processing block diagram, and get a bit file from that drawing? Luckily, yes. So let's get started. In our previous video, creating a custom RFNoC FPGA design, we demonstrated a text-based approach to creating a custom FPGA design using an I-provided FPGA blocks. I'm assuming that you did already watch this video. As of UHD 4.8, we can do the very same thing graphically using GNURadio companion, and we'll walk you through how to do that in this video. First, we'll introduce the image core GRC file that describes the FPGA design in terms of a flow graph. We'll compare it to the image core YAML text file and explain its elements. Then we'll show how to trigger a bit file compilation from GNURadio companion. And finally, we demonstrate how to modify an existing design by adding an FFT block to it. We'll not show how to deploy and validate a bit file, as these steps are identical between both workflows. Also, we assume that the UHD driver, Xilinx Vivado, and GNURadio companion have already been properly installed. And you can find the recommended version below this video. We start from the same shipping FPGA design for user PX410 that we've modified in our previous video. Again, our goal is to statically add OFDM modulation, so that is FFT and cyclic prefix handling, right after the sample rate conversion blocks, where the green box is. So the target FPGA design would look like this. We've added a dual channel FFT and cyclic prefix removal into both receive path, and a dual channel IFFT and cyclic prefix addition into both transmit path. So first of all, let's open GNURadio companion. Then we'll navigate to the standard FPGA designs for user P that are installed with the tool. At this point, we provide two designs out of the box that can be used as a starting point, one for user X310, and one for X410. As we want to modify the standard design, let's first create a copy of that. And next, let's open the copy for editing. So the first thing we want to do is to reorder the design so that we can more easily compare it to the signal processing block diagram. The result should look like this. Now let's compare that with our block diagram. We can see that the FPGA image is almost completely identical to the block diagram, which is the beauty of the graphical approach. Also note that the crossbar is implicitly added by the underlying tooling, similar to the text-based approach. Now, how does the FPGA design in GNURadio companion relate to its text-based counterpart using an image core YAML file? Let's compare both approaches side by side. The image core YAML file starts by setting general parameters. These are defined as part of the board support package. The corresponding block in GNURadio companion is the RFNoC device board support package block and its configuration options. The Ethernet transport adapter is defined in an inherited file in the image core YAML. It has a block representation in the image core GRC file. Likewise, the streaming endpoints and the NOC block sections have a block representation each. The static connections and the clock connections are represented by wires in the image core GRC. So both approaches are very similar. If you're familiar with one, it's very easy to switch to the other. I'd like to point out a few things that are slightly different compared to the text-based approach next. For instance, the options we would set for the RFNoC image builder tool on the command line can now be set in the options block. The minimum we need to define is the output, that it's an RFNoC bit file, and we need to point image builder to the FPGA directory in the cloned UHD repository. With these options set, we can already trigger a compile of the shipping image core GRC designs. So let's do that by pressing the F6 key or by clicking Execute the flow graph. A terminal window will open which shows the compile progress, and this terminal window will close automatically once the compile process completes. So the compile is done. Where can we find the results? Recall that we did not specify the build output directory in the options block. Hence, we can find the bit file and the device tree overlay file in the exact directory where the image core GRC file is located. Let's have a closer look into the other blocks on the diagram next. The board support package block provides access to clock signals and I/O. It also allows to configure a couple of parameters that we explained in our companion video already. A parameter related to the board support package needs to be set in the variable block. The number of samples per clock must be selected as defined in the board support package file as a function of the RF bandwidth. The RFNoC radio block allows setting of parameters such as the number of ports per radio block. Also note the use of the parameter SAMPs per clock that we've just discussed. We need to ensure that each block is assigned a unique alias in the Advanced tab. And finally, block functionality and parameter definitions, they can be found under the Documentation tab. DDC, DUC, and stream endpoints, they're all configured through very similar parameters as compared to the image core YAML file. Finally, for the Ethernet transport adapter, we can select between different Ethernet configuration options. And please note that only a subset of these options that can be selected are actually valid. Now we'd like to add the FFT block. First, we need to remove the replay block to free up FPGA resources. We find the RFNoC blocks that can be used in an FPGA design under UHD, RFNoC Image Builder, Core and Blocks. Also note that under UHD RFNoC you'll find the host correspondence for each FPGA block, but we'll don't need these during the FPGA design. So let's pull an FFT block onto the diagram. First thing we'll do is to add a unique alias. Then we configure it to support 2 channels and remove the cyclic prefix removal logic, as this block will implement an IFFT in the transmitter. Then we connect the FFT block to the stream endpoints, the DUC, and the compute engine clock. And finally, we repeat this procedure for the other IFFT and FFT blocks. The final design should look like this. The FFT block is highly compile time configurable, and you can find the meaning of the different parameters under the Documentation tab. Now, the only thing left is hitting the compile button and start using the FPGA image. This video concludes our initial series about creating custom bit files in RFNoC using existing FPGA IP blocks. There are more ways to create custom bit files for user IPs that we may cover in the future. We started with the basic principles of RFNoC. Then we discussed the YAML file format to describe an FPGA design. We showed how to modify and compile an existing design. And finally, we demonstrated the same workflow in a graphical design environment. The text-based approach on the right provides you low-level access to all design details, while the graphical approach on the left is useful to get started, especially if you're used to signal processing block diagrams. It helps you to develop a very intuitive understanding of the bit file functionality and its signal flow. So let's get started with your own design.